in this short lecture, I will give a brief introduction to the theory of cyclic algebras. So let capital F be our field, and let's consider a cyclic Galois extension of F of degree n. Let's also consider a generator of the Galois group of this field extension, so a generator, and also an element beta, invertible element of F. So given all this data, we can define the associated cyclic algebra. So these cyclic algebras were introduced by Dixon in 1912, so 100 years ago, more or less. And they are defined as follows. So you consider this cyclic Galois field extension, this generator of the Galois group, and this invertible element. So as you consider the following vector space, where you have following. So this is n-dimensional K vector space with bases given by 1, j, etc. until j n minus 1, where j is a formal symbol. And now on this vector space, we can define the multiplication, and using distributivity, it suffices to impose the following relations, so that j n is equal to beta, and the other relation is that lambda j is equal to j, and then the action of the generator of the Galois group on lambda, and this for every lambda for every in capital K. So we impose these two relations, and with these two relations we have a well-defined multiplication. And the important remark about this definition is that this cyclic algebra, it's actually, so it's a n square dimensional F algebra. So note that it's not a capital K algebra because of this relation here. It's an F algebra, not a K algebra, and it's n square dimensional. And this definition actually generalizes the quaternions. So let's see why is that the case. So an example are the quaternions. So the claim is that if you consider this cyclic Galois field extension from the complex numbers and the reals, and you consider for generator of the Galois group the map that sends I to minus I, in other words, the conjugation, and you take for beta minus 1, then this is actually isomorphic to the Hamilton's quaternions. So one simple way to see this is as follows. So I recall you that the quaternions are of the following form. So a quaternion can be written as A plus BI plus CJ plus DK, where A, B, C, and D are reals. So you can rewrite this as follows. You can rewrite your quaternion as two complex numbers. So Z plus WJ, where the Z will be A plus BA, and the W will be C plus DI. So, and this with Z and W, now they are complex numbers. And so you actually get, instead of a four-dimensional basis of a real vector space, you get a two-dimensional C vector space with bases. So now the basis is given by 1 and j. And with these bases, you observe that the multiplication here, is given by, so the j square gives you -1, and then when you take, you have this commutativity here, and this for every scalar now in C. So you see that in fact they are isomorphic. It suffices to identify the I here with the I here, and the j here with the j here. So it's another way to think about the quaternions using complex numbers. Okay, and more generally, they not only generalize the quaternions, but they generalize the quaternion algebras. Let's see another example. Quaternion algebras. So now we are in the case where the characteristic of f is different from 2. So suppose that you pick 2 invertible elements in f, and let's assume that alpha is not a square, so that it's not a square. If it would be a square, we know already that the quaternion algebra is just 2 by 2 matrices on f. And now there is a similar argument as above will tell you that if you look at this cyclic algebra, where you take the extension of f given by adding this square root of alpha, so you have this extension, and you take the generator of the Galois group given by sending the square root of alpha to minus the square root of alpha, and you take beta, this element, then this will be isomorphic to the quaternion algebra, and the isomorphism will correspond, the I here will correspond to the square root of alpha, and the j will correspond to the j here. So they actually generalize quaternion algebras. And well, let's see another example. So suppose that we are in the case where the characteristic of f is different from n. So n in this case is the degree of our extension. So in here, and suppose also that we have 2 elements, alpha and beta, 2 invertible elements of f, and now we impose that alpha is not now power n of an element. So a generalization of the previous example, this assumption. And now let's also choose a primitive root of unity, let's call it like this, of your f. So let's suppose that f has all roots of unity, so a primitive nth root of unity of f, okay? So now it turns out that if you look at this cyclic algebra, where to f you add this root over f, and then you take the generator by sending this element to the w n alpha, sorry, here it's n, and you take for element beta, then this turns out to admit a more explicit description given by the F algebra with 2 generators, and where you have this relation where the power n gives you alpha, the power n gives you beta, and then they commute up to W. So you have such a thing. So it's clearly a generalization of the quaternion algebras that you get if you consider this particular case of cyclic Galois field extensions. Okay? So you see that cyclic algebras, they extend the quaternion algebras. And the important fact here is that the cyclic algebras, they are always central simple algebras. So it's a central simple F algebra. So now one may wonder, are there central simple algebras which are not cyclic? Because this class of algebras seems to be pretty general. And the answer is no. I mean, the answer is yes, there are central simple algebras which are not cyclic, but that actually depends on the field. So let me just mention this famous result of Brouwer, Asse, another from 1932 that says that every central simple Q algebra, so if you are over the rationals, is isomorphic to a cyclic algebra. But over other fields, this is no longer true. So in fact, this class of algebras does not give us all possible central simple algebras. If you want to learn about a possible generalization of cyclic algebras, stay tuned for the next lecture.